Okay, so what did we talk about last time? Each day I ask this question. Each day, no one has thought about it before they get here. So what did we talk about last time? Kelvin-Helmholtz, instabilities generally. So what are some of the aspects of how we estimated the instabilities? What are some of the important features of what makes it easy to do the calculation but also limits what the implications are? Linearization. So the linearization comes in a couple of different forms. One part is so there's a Fourier transform assumption here. Fourier transform in x and time, and then we didn't do a Fourier transform in y to begin with, except then we did do a Fourier transform in y for this equation because away from this interface, it is actually homogeneous in y. By homogeneous, I mean none of the flow parameters, which here is only the shear, depend on the y variable. So in this Kelvin-Helmholtz situation where you have just an interface, you can solve the bottom half plane and the upper half plane as though there was no variation in the flow, and you just need to get a matching condition to match the two linear solutions together. So that's basically how this goes. So here's the linear solution to this equation for the pressure above and pressure below, and then here's the way that the velocity is related to the pressure. Here's the matching condition, which basically says that the interface between stays on the interface. So those are the pieces of that. And then here is the dispersion relation that comes out of it, or the eigenvalue equation, or, yeah, those are the two ways of describing this. So what does this tell us? How do we interpret that? Which ones are the fastest to grow? Large wave number, smallest modes, and in fact there's no cutoff at all here. So the smaller you are, the faster you grow, is all this says. And if the velocity shear was bigger, you would be growing faster as well. So that's a pretty simple, kind of intuitive thing to do. It's less intuitive when we get to the other classes of instability. So what are the limitations because of linearity? Or what's the advantage of linearity? Either way.
It's not representative of reality.
It's not representative of reality because we know that the other advection term, the prime-prime advection term, will become as big as this term as soon as u prime becomes as big as big U. So pretty soon, the perturbations will be as large as the magnitude of this flow, and then the linearization is no longer appropriate. What's the key advantage we got from the linearization in terms of the Fourier transform method? We have a sum here, but then we don't really have a sum here. Why? How do we get away with that? Exactly. In the linear system, the different modes are not coupled in these equations because there's no product of one with one k and one with another k. So the key new thing we're going to see when we get to turbulence is that turbulence is the opposite end of that. It's not gentle contact between neighboring wave numbers. It'll be very strong contact. In fact, one way to think about turbulence is it's the limit when the linear instability theory has been forgotten and each wave number is driven more by its contact with other wave numbers than it is by its own instability. So that'll be a transition we make as we start to think about turbulence. So in some sense, the linear instability is useful for small amplitude problems, early time, but it gives us a sense of how big things are and maybe what's important about the flow, like how fast the flow goes in this case, which is not a very interesting thing because it's the only thing in the flow. But we'll see when we get to baroclinic instability that actually tells us quite a bit about the size of the phenomena and the speed that we're thinking of. But the turbulence case is the opposite end, where the size of the instability is forgotten and wave numbers are contacting other wave numbers as their dominant mode of being energized. So those two pieces are the interesting ends. In the oceanic mix layer, the strong turbulence, the small scale stuff, really goes like the strong turbulence. It no longer really has much of a remnant, even though it may have originally been something like a Kelvin-Helmholtz or shear instability to begin with. There is only one slight contact between the shear instability theory and the turbulence, which is the instability limit. So in this case, there's always an unstable mode, but we started talking about necessary conditions for instability. If the necessary conditions for instability are not satisfied, then we just don't get turbulence. And so that necessary condition becomes a useful cutoff for when we expect to see turbulence or not. But once we see turbulence in the ocean boundary layer and the atmospheric boundary layer, the scale of that turbulence evolves and becomes very strong, and there's lots of nonlinear connections between different scales, so these are forgotten. The exception to that, which we're going to talk about at the end today, is the submesoscale, where partly because things are onsetting and turning off and turning on, and the submesoscale is sort of intermittently present, the size and speed of submesoscale features still resembles its linear instability case, even though it does evolve beyond that. So we'll see that's sort of an interesting limit. Okay, so then we went to parallel shear flow, and in a more general parallel shear flow, we found the Rayleigh equation, and then remember this was a lab experiment, which just shows you, so this is basically what the linear instability describes. This is what comes next. This is definitely not linear anymore because it's wrapping up. So if wrapping up, what does that mean about the perturbation velocity versus the mean, the shear, the little u versus big U? They're almost the same. If this can go, if this can wrap itself up, it means that the perturbation is as large as the background flow, essentially. So we are no longer linear at that point. And in fact, this doesn't look anything like the linear instability wave number, pure wave number kind of case. Okay. So this one we jumped over last time. So let's go back and see how this goes. So we found the Rayleigh-Kuo equation. And then here is a jump condition, which we're going to see what that comes from in just a second. This and this, which goes along with it. In the general parallel shear flow case, we couldn't say a whole lot except to say we did this vorticity equation, and that became the Rayleigh-Kuo equation. So here you have two derivatives of the growing stream function in y. And here is the background shear profile, two derivatives in y. And so if it's a nice smooth profile, you can calculate this, and then you can do eigenmodes and come up with this, figure it out. You can find the C and the K relationship, so the dispersion relation from looking for solutions to this mode. But that's actually rather hard to do without a computer for most interesting profiles. An alternative is to take piecewise linear profiles of shear. So one example of piecewise linear was the Kelvin-Helmholtz case. So how did the solution of Kelvin-Helmholtz get simpler because of how did it work? We solved down there and we solved up there. How? go back. You want to see? So we have this condition, and then we got these solutions. How did that work?
It does not go to infinity.
It doesn't go to infinity, and since U doesn't vary, it's just a simple homogeneous equation. So we don't have to worry about some abstract function of y that we have to write ODEs and solve. We can just say, oh no, it's just an exponential decay. It's the simplest case. It becomes a homogeneous constant coefficient differential equation, which we can just look up the answer to. We don't even have to do any integrals or anything. And then all we had to do was match those conditions across the interface. So look at the piecewise linear and look at Rayleigh's equation. So what's special about the piecewise linear? It doesn't depend on y except linearly. And look, there's only a second derivative of u appearing in this equation. So this is 0 again. So we will have, this equation will be constant coefficient homogeneous differential equation, and so we can solve with our standard Fourier transform kind of tricks, and it will be very easy to solve this. What will we have to do with these kink points?
You can do it on 3 regions, top, middle and bottom.
And then what do we have to do to get the next step?
I think they will match automatically at the interface.
Well, they don't match automatically. That's exactly what this guy is telling us about. So you have to match something as you cross across these interfaces. And since I don't think we should really dwell on how to solve these things in great detail, we talked last time that this can always be done. But I don't really want us to dig too much into the algebra. We're not doing a whole lot of homeworks on this or anything like that. But basically, you can integrate this equation and get a jump condition, which then is satisfied if you get this case. So you could make these into jump conditions, and in this case, if you do, take this jump condition, plug in and go through the solution for this profile, you end up getting back the Kelvin-Helmholtz solution. So you can do Kelvin-Helmholtz this way by taking the Rayleigh equation, integrating it once, getting a jump condition, examining that profile. But we could have looked at lots of other linear profiles if we wanted to too. So it's sort of a nice simplification. If you wanted to do a final paper on instabilities, there are many, many papers describing different kinds of piecewise linear instabilities, which is kind of a nice thing to think about. But as I said before, the linear instability doesn't really help us much in the fully turbulent flow except for the necessary conditions. So I want to spend a little bit more time thinking about what the necessary conditions are for turbulence. So we have the Rayleigh-Kuo equation. We can solve that and get an answer. But a different way to go about things would be to take the vorticity equation itself and try and figure out something, give me a solution to this equation. How can I guarantee whether that solution is growing or not? Are there certain times when I can say there's no way possible for any solution to exist without knowing much about the details about the flow? That's what the necessary condition is. So necessary and sufficient conditions are not quite the same thing. So a necessary condition is something that must be true if there is to be an instability. A sufficient condition is something that when it is true, then there will be an instability. So a necessary condition is a little bit weaker. It is possible that you could have the necessary condition satisfied but not see an instability under weird problems. Like there are lots of pathological problems that mathematicians love to find where that's true. That's not what we're going to focus on here. We're just going to recognize that the necessary conditions are a useful guideline. And in fact, under most of these kind of classic shear flow problems, with a few weird exceptions, the necessary conditions are also sufficient for a prediction of when turbulence happens. So if you satisfy the necessary condition, you'll get an instability, it'll turn into turbulence. Okay? All right, so how does this go? So here's our vorticity equation. Remember, Z is UYY. So, or Z is UY, sorry. So this term right minus UY. So this thing right here is this. So we can multiply this equation by zeta squared over QY, where QY is now this again. Why Vallis likes to change. He's not happy with any notation for this term for some reason. So every equation he writes it with a different notation. But anyway, QY is this coefficient of V. And if it were, so I claim that if this equation is basically this one just multiplied by zeta squared and divided by QY. You get from that equation to this equation. So we can see the divided by QY there. Zeta squared comes because we have zeta times d zeta dt, which is 1/2 zeta squared. Zeta squared here is zeta times d dx of zeta, so 1/2 d zeta squared dx, which is this one. And then V, and then there's multiplied by zeta, and where's the 2 come from?
The other two terms at 4.
Hush. Yeah, the other 2 terms on 1/2, so it just puts it on there. Okay, so that's where this comes from this equation. So what kind of an equation is this? Yeah?
Why is the QY in the EDT?
Oh, because he wants it to be something that's steady in time. It's a background flow, and so he just pulled it in.
Right.
He's writing an equation for this object, which for other very obscure reasons, this is the object you actually want to think about. But from our perspective, it's just this is tidy. Okay, so what kind of an equation is this if it's an equation for zeta squared? If this is an equation for the vorticity, this is an equation for the vorticity squared. If I took the momentum equation and I wrote an equation for the momentum squared, what would that be? Energy. So if I take du dt, u dotted into that, and I write an equation for d by dt of u squared, this is the energy equation. In a very similar way, if I take zeta d zeta dt, and I use that to write an equation for zeta squared, that's called the entropy, which is almost like just a made-up word. It sounds a lot like energy, but then it has some funny stuff in the middle, which is what they literally want you to take. This is the squared invariant that comes from thinking about vorticity. And in 2D and in quasi-geostrophic flow, there is actually a conservation principle for entropy. So we've been talking about 2D flows here. At this point, we're thinking about 2D incompressible flows, in which case entropy is actually a conserved invariant of the flow. How do I know it's a conserved invariant of the flow? Because we just wrote down an equation which talked about it being conserved. I could have done a nonlinear form of this and gotten a nonlinear equation as well. But entropy is playing a key role here. So everybody, we're going to talk more about entropy as we learn about turbulence, because thinking about energy and entropy as simultaneously being conserved is a really important part of understanding two-dimensional and quasi-geostrophic turbulence. When we get to that, I just wanted to point out that it's part of this. Okay, so if we're going to have an instability that grows, what can you say about entropy, knowing that dq dy doesn't change in time? If we have an instability that grows, what has to happen to the entropy?
From that equation, I think it is decaying.
It could decay. In this balance, it could grow, but it definitely has to do something. If we have an instability that is changing its amplitude, entropy would have to change with it. Does that make sense to everybody? So this is just, from our perspective, this is just a quantification of entropy being an important descriptor of how big the growing mode is, and it might go up or it might go down. It's a little easier than vorticity to think about. Why is that? Is vorticity of a single sign? No. Vorticity could be either cyclones or anticyclones, and so if I know that the vorticity is positive, I don't really know much, but if I know that the entropy is positive, I know that, and getting more positive, then I know that the amplitude is growing. So this is a sign definite thing to think about, which tells you about how big the magnitude of the perturbations is. So from this perspective, that's all we need to know. Okay, so what happens if we integrate this equation in x? We get this, which is just the integral of this with respect to x. We get this. And what happened to that term? Boundary condition. So u and dq dy don't depend on x. Why not?
There's no variation, non-constant.
There's no variation in the x direction. We're talking about plane parallel flow. And so the x direction is the direction in which nobody's varying, except for maybe the instability, but not the background flow. So these are just constants in x. So now I'm talking about the integral in x of something that's a perfect derivative of x. From left to right? Well, I don't know. What do we want to say? From 0 to infinity, or if it's periodic, 0 to 2 pi. But in all of those cases, you're getting zeta squared evaluated on the left side and the right side. So let's go back and think about that. No variation in x. What do we do for the x variations in all of our solutions? Oops, this is also not the right slide. What do we say about the x variations here? Periodic cosine. So if this is going from 0 to 2 pi of something that's periodic, what's the answer? 0. If I was going from minus infinity to positive infinity, if I didn't want it to blow up, I would also have 0. So essentially what's happening is that this term is vanishing because of the boundary conditions together with the fact that it's a perfect x derivative. So, all right. Okay, so this term is left over, and then Alice does some fancy footwork to show you that this term is equivalent to this. This is basically remembering that the vorticity is the curl, and then you use a calculus identity to write it down like this. So there's a ddx part, v squared minus u squared. What's going to happen to that? That's going to be 0. What about this guy? Don't know yet. But if we integrate by y as well as x, then it becomes 0 for the same reason. Because you're either going to infinity in the y direction, or you're going to some solid walls where either u or v vanishes. For whatever reason, this one is gone. So if I take this equation and integrate in x and y, that is, take it over the whole domain, what does this equation tell you? The rate of change of this object is conserved. This isn't quite the entropy. It's the entropy divided by dq dy. Okay? So if the entropy is going to grow, can dq dy be constant? No. So this is where, really, again, smart guy that he was, he figures out that this is, in order for the entropy to grow, it implies constraints on dq dy. The shapes of dq dy are limited in order to arrive at a condition where ddt of zeta squared on average over the whole domain would be positive. Okay? So the way that it gets stated is a necessary condition for instability is that the expression dq dy or beta minus uyy must change sign somewhere in the domain. So what happens if it changes sign? If it's positive everywhere, it's like a weighting function for ddt of zeta squared, but if zeta squared wants to grow in time, zeta squared is positive definite. If this thing is positive definite too, the integral is positive definite. We can't have ddt equals 0 and have that one growing, because this thing is fixed in time, remember. If it changes sign, then what happens? What's possible? Let's draw a profile. So I don't know what the profile looks like. Well, let's say that qy is greater than 0 here, and qy is less than 0 here, and our zeta squared profile does something fancy, but it's growing in time. So if I evaluate zeta squared divided by qy up here, what do I get? A positive. And down here, I get a negative. If qy changes sign, I can grow zeta squared here and grow zeta squared here as long as I'm balancing the amount of zeta squared per unit qy in both, which allows me to still get this condition satisfied. Does that make sense to everybody? So this is called the Rayleigh criterion for stability, actually, is what they normally call it. So you can flip this the other way and say, if this is not true, then you have a stable flow. And so Vallis challenge gives you a whole page. Let's look at these. Okay, here are different U profiles. Are these, here's U, and here's UYY. Which one of these are stable? Is this one stable?
Yeah.
Yes, because it's always negative everywhere in the domain. So I can't balance the negative part and the positive part canceling out and allow zeta squared to grow. So if you put, this looks like it would be an unstable jet. So you put that in a flow and you're like, that's probably going to be unstable. It actually isn't. This would be stable at any amplitude for all time. What about this one? It looks an awful lot like that jet, except it has these little reversals. There's an inflection point here and here, going from curvature that way to curvature that way, concave this way to concave that way. And what does that do to the sign of UYY?
It's
It's
unstable.
unstable. So sometimes this is called Rayleigh's inflection point criterion, because an existence of an inflection point, that is where the curvature changes from one direction to the other direction, is the same thing as UYY changing sign somewhere in the domain. So it's an inflection point because the inflection point means that you have different signs of UYY. What about this one? Two jets next to each other. Looks an awful lot like this jet in both of them. Is this going to be stable or unstable? Or potentially unstable? Potentially unstable because it's got two different signs. So this jet on its own is stable, but if you put a little curvature on the edges, it would be unstable. If you put two jets next to each other, even without the little curvature on the edges, the existence of two jets could be unstable. And then what about this guy, which isn't even a jet, it's two jets on the walls. Potentially unstable because there's an inflection point right here. You don't have to have two inflection points, you just need one. Okay? Does that make sense to everybody? Okay, so that's 2D incompressible. And in 2D incompressible, we talked about entropy, because entropy is sort of the measure, because if I'm incompressible, the only thing that can move is vorticity, so the vorticity squared is a useful measure of whether there's any motion there. Now we'd like to think about baroclinic instability. This is a 3D instability of a geostrophically balanced flow. Okay? So if it's a geostrophically balanced flow, what are our equations of motion we could go to that would be simplified rather than the full Boussinesq equations? Potential vorticity is conserved, and we could do it either in the planetary geostrophy system or we could do it in the quasi-geostrophic system. We're going to do it in the quasi-geostrophic system. It's interesting to think about the distinctions in this problem if you don't. But okay, so here's the idea. So now we're looking, it's still a plane parallel flow, but it's flowing this way. And then we have low density and high density. So what does low density next to high density mean? What relationship are we thinking about for geostrophy? The thermal wind. So if we were accumulating pressure, it would be accumulating more quickly over here than here, which means that there's a pressure gradient this way and a pressure gradient that way at the top. And so there's a shear and a rotating plane. So on the F plane, we would have a sheared flow, thermal wind flow, and something like this. So the first thing that Valis wants you to contemplate is whether this is stable or unstable to just swapping parcels. If I take this point A and swap it with point C, what should I expect to happen? Which one is more dense? A. So if I try to lift A up to C, it'll find itself more dense than its environment and it would fall back down, right? That's sort of like our inertial oscillation or internal wave case. What about if I could somehow manage to swap B and A? Is B more dense or less dense? More dense. And which one is higher up? That's a really stupid question, but which one is at a higher Z? B, right? So potentially I could get potential energy out if I could figure out a way to swap B for A, because I would be taking something heavy and lowering it in Z. It's a little trickier if you do it in pressure coordinates, but it still works out to be the same deal. Okay, so I could take something from low pressure and put it at high pressure and do that. So that can't necessarily always happen though, because I've also got this complicated shear flow, and so it might cost me more kinetic energy in trying to swap those parcels, and I would end up losing energy anyway. So, because if I swap this, and they conserve their momentum and their energy, when I swap them, I'd have to have a balance between changing the kinetic energy structure and changing the potential energy structure. I'd expect it to be unstable if what happens? If I swap A and B, and I change the kinetic energy and change the potential energy in doing that, when would I expect to have an instability? If the energy at the end was what related to the energy at the beginning? Yeah. So if I can manage to do this arrangement, it might cost me kinetic energy, but I'd gain some potential energy. But if the potential energy gain was greater than the kinetic energy loss, I would expect there to be an instability. This is basically the argument that allows you to figure out whether symmetric instability exists or not. It's also inherent to baroclinic instability, but baroclinic instability is very complicated. The pattern that it does to try and swap those parcels around is pretty complicated. Okay. So, we've got our good old QG equations. We can do it in 2 layers, or we can do it in the continuous form, or we could even do the shallow water equation, but we have to do 2 layers at least, because this instability requires 2 layers. And how do I know that it's 2 layers from this little schematic? At least 2 layers? We need 2 different energy levels, or 2 different densities. So we have to have at least 2 layers. We're actually going to do it in the continuous case because that looks more like Rayleigh than the other one. The 2-level one. This is called that problem in the simplified form is called the ED problem, EADY, and this one is called the Phillips problem in 2 layers. And if we neglect, the ED problem is neglecting the beta term. If we keep the beta term in, then it's called the Cherney problem. But there's sort of 3 classic instability problems that have to do with the QG equations. Why should I be a little worried about using QG equations? We have a thermal wind. That's great. QG equations can do that. What's missing from the QG equations? What phenomena gets removed when you go to QG from shallow water equations?
Vertical velocity.
The vertical velocity actually is sort of still here, partly in the continuous form, but we talked about so in geostrophic adjustment, we have 2 different kinds of things. We have waves, gravity waves, and then we also had the geostrophic flow. In the quasi-geostrophic system, we don't have the gravity waves anymore. We just solve for the geostrophic flow. So why is that a problem for an instability problem? It could be unstable in the gravity waves, but stable in the geostrophic flow, which it turns out this system actually is. So the ED problem, there is another branch of instability that you can't access from the quasi-geostrophic equations, which is the symmetric centrifugal instability branch, which we're not going to talk much about it for the moment, but we're going to come back to it. When we switch to study this problem in the QG equations, we're only talking about geostrophic instabilities. So that will have a different set of constraints. Yeah?
But when we just discussed the necessary condition, Qy is constant at time, then if we have gravity wave, it will change with time too.
Yes, but that would only be the growing instability. So imagine, in we don't even have to imagine, the Kelvin-Helmholtz flow, the background flow is steady in time, but the waves that grow are actually gravity waves on a Kelvin-Helmholtz flow if the lower shear is denser than the higher shear. So if I put a flow like this, and I make this denser than this, I could still get a Kelvin-Helmholtz instability on that interface. That instability would actually be a growing gravity wave. If I tried to set up that situation in the quasi-geostrophic equations, I would find that it was stable.
So you mean the mean wind we used in necessary condition is still the geostrophic flow? Not
Yes. So the mean and the perturbation, when we do this in the quasi-geostrophic equations, will both be solutions of the mean, steady case, and the perturbation will both be quasi-geostrophic perturbations. What I mean is that if I use the Boussinesq equations instead of the quasi-geostrophic equations, I might find there were other instabilities that had other conditions for that. So there's the possibility that we're missing something by switching to QG. And in fact, not only the possibility, there's the reality that we're missing something in this problem by switching to QG. Okay. But let's write down what you write down if you go to QG. So which equation is this? Conservation of potential vorticity. So here's our perturbation potential vorticity. Here's our background potential vorticity that's in that thermal wind flow. Here's our thermal wind velocity. And here's our perturbation velocity. Q prime, we can write it as a stream function, which has two parts. There's the part that's due to stratification, and then there's the part that's due to the relative vorticity, just like we talked about with QG. And then we have a buoyancy equation at the boundary. Remember, this is not enough to solve this because we can't invert from the stream function, from the potential vorticity back to the stream function because we have z derivatives over here. So we needed a z condition. And we talked about that being the buoyancy equation solved at the top and the bottom. Okay? So we have to solve these two equations together. This one is the field equation in the middle. This one is the boundary condition on the top and the bottom. Okay, so here's the boundary condition at the top and the bottom. Here's the field equation in the middle. And we can write the stream function to vorticity relationship just like we always did, except now it's linearized. But it was already linear. It's just we're writing primes on everything to make it clear that everybody has a perturbation. Which term is missing up here from the linearization? V prime Q prime, essentially. Yeah, the little q. So the one that looks like this but with a prime here, and the one that looks like this but with a prime there. So this is a linear perturbation. Okay. If you take this and then try to write it in the same form as the Rayleigh equation, you find this condition comes straight out of this together with this, plus these at the surface and bottom. So essentially the difference between this and this is just that he's written the buoyancy is d psi dz. Buoyancy is d psi dz. And this one, that psi yy is coming from here, psi zz is coming from here, k squared psi is coming from the x derivatives in here, qy psi is just that one, okay? So these look an awful lot like the Rayleigh equation. Remember the Rayleigh equation was our condition on the vorticity. This is the potential vorticity budget, and here's the buoyancy budget, and it looks really similar. So what do we expect to find if we look at the necessary conditions for growth from here versus there? We should find almost the same piece? No. There are some simplifications which help you not go crazy. This is the ED problem, so it's F plane, stratification is constant, the shear is constant, and the motion is contained between two rigid layers. That's a simpler case. And in that case, we can actually go ahead and solve the linearized problem all the way through by just looking at this equation and this equation. We can plug in, boop, 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 boop. So, or whatever. This part is not so important, it's just algebra. We find that the growth rate is maximal at 0.31 times the shear divided by the deformation radius. So how is that different? That's the maximum growth rate. And the x wave number, so your k, remember, if we go back to Kelvin-Helmholtz, oops, the growth rate just got bigger the smaller the bigger the k was. We're not finding that. We're finding something different in the ED problem. We find that the growth rate is maximum at some wave number, and this is the x wave number per unit deformation radius. So k times LD. There is a fastest growing mode, and its a size is right near the deformation radius. So what does that tell us? in the ED problem? If we have an instability, what's it going to look like?
It will flatten look like a single kind of wave.
It'll look like a wave, and its size will be about the deformation radius. So once again, just like in geostrophic adjustment, the deformation radius just popped out naturally. In the ED problem, the deformation radius pops out naturally as a scale for the instability. So the fastest growing mode is near the deformation radius. It's not equal to the deformation radius, it's just nearby. The growth rate is also governed by the size of that thing. So K is linked to the deformation radius. So if you want to know how fast it grows, it also scales with the shear, but the deformation radius. So what we've done essentially is do a problem that's really similar to the Kelvin-Helmholtz problem in that it's a simple plane parallel shear, but what pops out is the deformation radius scale is the critical scale. And these are more complicated things that I don't think we want to talk about today. The last piece I want to close on, this is a bunch of stuff about the scales. We'll come back to that next time. You can play the same game that we did looking for the inflection criteria, and you come up with a more complicated version of the inflection criteria that's appropriate for quasi-geostrophic instabilities of a plane parallel flow. One of them looks awfully like the old one, except now it's not the UYY, it's actually the potential vorticity gradient. It changes sign. Or you can have these funny things that connect to the boundary conditions because of the auxiliary equation from the buoyancy at the upper and lower part. So we're going to go through this a little bit more next time and think about how the ED problem, which one of these gets triggered in the ED problem. This is the Rayleigh inflection point criterion. This is the Charney-Stern-Pedlosky. They don't call it the inflection point criteria because these are not inflection points. Only this one is. But there are other ways you could be unstable in the quasi-geostrophic system more than in the 2D instability problem. It has other interesting variants for that flow. Okay? So next time we're going to talk, we have the homework's coming through, and we're going to talk about questions on the homework. We'll get ready for the peer review for next time, and we'll finish up this stuff.
Homework's about Ekman pumping, but we did not talk about.
Oh, that's true. I forgot. Let's skip the Ekman pumping one. Let's put that on the next homework. We'll repeat that one. If you've already done it, great, you can turn it in. But we'll pass that one to the next homework. That's probably easier than what we're doing because I want to talk about it in more detail. Has anybody solved that problem yet? No. Okay. We'll just postpone that one. It'll be on the next homework. Okay? So you can skip the problem of the Ekman pumping for now. It'll be on the next homework.
There are two. Yeah, there are two.
Are there two problems? Both of them will be on the next homework. So it's only the other three problems. Three problems this time. Yeah.
It seems for the really inflection point theorem, we assume the periodic boundary condition.
Mm-hmm.
And for this necessary condition, actually the last three are all about, sorry, that last, from 2 to 4 are all talking about the boundary condition.
So it's even more complicated because those are about the upper boundary condition. So they're about the boundary condition on this surface and this surface. The Rayleigh one is like the vertical integral. So its only boundary conditions are on those side walls. So it's the boundary condition in the other direction, not the shear direction, or it's in the vertical direction of these boundary conditions. Whereas the Rayleigh problem was just 2D, it doesn't have a vertical direction, there's just the shear direction and that's it.
Then do we still assume a periodic boundary condition on the boundary boundary?
Yes, you don't have to assume it, you can also have, it's the same game where you can go to a very large domain with a regional shear, it doesn't matter which one you have. But it's periodic in the along flow direction, and then it could have rigid walls or whatever you want on the other side, but it doesn't change the criteria.
I see. Thank you.
And even if you have viscosity, which is an interesting case, you can go back and do this. Viscosity also doesn't change these. You still have to have these. So viscosity can damp some of the modes and make the some of the necessary conditions become more stable. So you could have potential instability in the inviscid case, but viscosity doesn't make it more unstable.